Okay, well, thank you all. I think we violated tremendously today the idea of, you need to fix the slides, by the way, they're being cut off, of having 10-minute lectures. So I appreciate you all. Hopefully you'll stay awake for this. I think it's a compelling subject. Just like we heard earlier about how Steve Lippard really feels very strongly about curing cancer, and how Lee Hood hopes that systems biology is going to solve chronic disease and hopefully infectious disease. I think one can make the argument that worrying about what we're going to do to make sure that the planet survives for future generations in terms of externalities of the environment and how we use energy and its impact on the environment is arguably as important. So I'm going to tell you about the Andlinger Center. Basically, I need to thank Mark Cardillo and the rest of the Dreyfus Foundation for inviting me. And Mark gave me very strict marching orders that I wasn't supposed to really talk about my research, but to tell you about the Andlinger Center and what we are doing at Princeton and how we hope that it will impact not just Princeton and Princeton students, but really impact the world. And of course, I will at least take a moment to tell you about my research, but I'll do that at the end. So this is actually a schematic of a building that it will be the Andlinger Center. It doesn't exist yet. Well, it exists in a shell right now. We will occupy it starting next summer. But lots of people have come up to me and said, "Oh, so when does the new center start?" And that enrages me because I've been working around the clock, 24/7. Starting many things. It's a virtual center right now, and so we have many things going on, even though the center doesn't have a physical home yet, but it will. So I don't have to tell anybody in this audience that there are many reasons why every university and anyone that is, especially chemists, I would say, have the ability with our tools and our expertise and our understanding to really make a difference in the problems and what those problems are. And of course, you can look both at climate change, as David Oxtoby mentioned earlier, but also even if you're a climate change denier, okay, which I hope nobody in this audience is, but even in that case, you can make the argument based on economic security, national security, that we have to be caring about our energy sources and the way that we use energy and its impact on the environment. And so, this is apple pie, I think, to most of you, that essentially we really do have to think about non-CO2 emitting solutions, energy sources. But as we do that, I mean, one could make the statement, gee, we should use biofuels. Well, but you have to worry in the case of biofuels about how much water we're draining from the aquifers in the middle part of the United States, and it's a very serious issue. And so you have to worry about the competition and the trade-offs between different energy technologies, their impact on water supply, impact on food, obviously corn-based ethanol being an obvious example of that. How do we store energy? How do we transmit electricity? And one of the things that's really clear is that, one could argue, gee, we should move to solar and wind completely, but there are two issues with solar and wind. First of all, they're generated in the Midwest and in the South, and that's where the fewest people in the U.S. live. And so you have to get the electricity out to the coast. Well, yes, there are ways of moving electricity using high voltage direct current lines, but the fact is that involves an entire infrastructure which in principle can be built, but the fact is that we have, and this brings up a very important issue, the way in which electricity is regulated in this country is not on a federal level. It is balkanized, and so you have to get so many different people in the room to start to make those kind of agreements. Basically, it's handled at the state level or multi-state level. There are many different regional transmission operators, and so policy is a huge piece of what is preventing us from moving toward renewable sources. In addition, of course, you don't get electricity when from solar if the sun's not shining, and you don't get electricity from wind if the wind's not blowing. So you have to make trade-offs. You have to think about the trade-offs between, do you build excess capacity? Do you have storage? And in fact, today we don't store electricity on the grid. To first order, we store none. So that's a real serious issue. Mentioned transmission, and of course efficient use. So these are all issues that that are critical for all of us to think. You can't just think about one part of the problem. You have to think about all pieces of the problem, and that's going to require R&D breakthroughs, and that's where everybody in this audience comes in, because the fact is that we can't go to the shelf right now and pull off solutions in every case that we need solutions. Some people may tell you the problems are solved, and they are not being truthful. So there's a lot of work that needs to be done. I basically woke up almost 8 years ago when I read the Intergovernmental Panel on Climate Change in 2007. I read the executive summary of the science report, and I thought, I've been asleep for 20 years. I'm not going to sleep anymore. I'm going to, which is actually true. But I am a microcosm of the United States in many ways. Basically, the oil shocks of the 1970s woke everybody up for a short period of time, and as soon as oil prices tanked, we all went to sleep again. And the renewable energy research that was done in the 1970s and in the early 80s during the Carter administration, basically, was a brief moment at which we made investments, and then we went to sleep again. And still today, the investments that we are making are nothing compared to what they should be, compared to the kinds of investments we've made in other sectors that can remain nameless for now. Okay, so we also need improved tech transfer. We need behavioral incentives. That's a big issue as well as economic analysis and good government policies. All of these things have to work together. And so that's actually the motivation behind the Andlinger Center. Now, why did Princeton do this? And why should Princeton do this? Okay, aside from being a university that has resources, Princeton is a very special place. Princeton has a history of being very successful at doing multidisciplinary research. It's small. People work together in teams very easily across disciplines. There's a natural ecosystem that's been set up at Princeton to do it. Why is that important? Because every single one of these problems that you can think about in terms of energy and the environment are multidisciplinary problems. They're not going to be solved just by chemists. They're not going to be solved just by physicists. They're going to be solved by a multitude of people working together. And so that is the natural place where where a center has value added, and Princeton knows how to do this in a very, very powerful way. In addition, Princeton prides itself on not just training experts, but training leaders. And there's many examples of that. I don't need to point out to you that the last 3 Supreme Court justices were graduates of Princeton, among other examples. So we know that we view that as part of our goal, of our responsibility to the world, to be training people with leadership skills and as well as the expertise. And then in terms of advising government, there are many people, of course MIT does it too and many other places as well, but there is a history from the Woodrow Wilson School of Public and International Affairs at Princeton of many people feeling that they want to use their expertise to either go and be a part of government. For example, Ben Bernanke, who I think everybody in this room knows who that is, was the chair of the economics department. There's many examples like that. So Princeton feels that that's part of our role too. Princeton in the nation's service and in the service of all nations is the motto, or the informal motto of Princeton. So the Andlinger Center, it's bringing together people that are scientists, engineers, people who are working on energy finance, economics, policy issues, as well as behavior. We actually just hired a postdoc to work on behavioral incentives, okay? And also the School of Architecture. It was founded in 2008. I became the founding director in 2010. A little time delay associated with my willingness take this on, among other reasons. Anyway, so that's what the center consists of in some ways. The mission is not a surprising one, to develop solutions, not just technological solutions, but policy options as well, to ensure our energy and environmental future. So that's the mission. The goals are as follows. We have 5 major goals. One is, again, it's all about value added, creating an intellectual community that engages people from many academic disciplines. So we have lots of activities to try to do that. Helping to accelerate multidisciplinary research. I'll talk about that to some degree. Training the next generation of leaders. And as mentioned earlier, what Princeton does is we have students concentrate in a discipline. So they do a deep dive into a discipline, but then they also have the opportunity to broaden out that in terms of context they may be interested in. We call them certificates. Princeton, to first order, has no minors. They have certificates that offer a coherent set of courses leading usually to a senior thesis in a particular area that is multidisciplinary. And I'm going to give you examples of what we're doing in the Andlinger Center with regard to that. Partnering with industry, with not-for-profit, also with government, to essentially get to practical technology and policy solutions. And you know, I don't believe in reinventing the wheel. We've done market research to understand, you know, how other places such as MIT and Stanford partner with industry. We then adopted that in a model that works for Princeton. I'll tell you a little bit about that. And I have a very ambitious goal to become the center the U.S. government turns to for information and advice. Of course, that's not really fair. They should get advice from many places. But we're trying to do our best to be helpful. I spent some time on Capitol Hill when I first became the director, and I asked staffers, I said, look, we're starting this new center. What can we do to be helpful to you? And the answer came back, we really need good information that we can absorb quickly, of course, that's what they say. And so what they meant is they want briefs. And so I took that idea and I said, you know, what I'd really like to do is find a way to distill down, wonderful chemical term, distill down to its essence, how different emerging energy technologies sit in reference to everything else. And so hence the name, the Energy Technology Distillates Project, which we started, and I will tell you about the first of that toward the very end. Okay, so this is Capstone. This is a list of Capstone programs. Okay, we have a highlight seminar series, as anyone would. You bring in people from all over the world to understand the state of the art in various energy and environmental areas, covering all sorts, from economics, policy, architecture, you know, you name it, as well as the usual science and engineering areas. We have over the last, 3-4 years, really only the last 3 years, we've awarded almost $2 million to faculty, to essentially faculty teams, where I've actually tried to do behavior modification on my colleagues. So what does that mean? What it means is that I've asked, we've set up these programs such that faculty have to pick someone to work with that's in a different field from them, to bring together people to think about problems in a different way. I firmly believe that that's how we will get breakthroughs in energy and environment, or really in any problem. When you bring new perspectives together, you have a better chance of coming up with a different answer, right, than you had before. So that's what we do. We also started a summer undergraduate internship program. It's modest. We've had 23 undergraduates working in faculty labs. I fundraised for and we have a graduate fellowship. We've awarded 4 of them so far that pays for a year of their research in energy and environment. And then I mentioned these certificate programs. We now have 2 of them, because one of them was started actually by my department, Mechanical and Aerospace Engineering, but for the entire, representing the entire School of Engineering. And it's called the Program in Sustainable Energy. And it's a technical certificate really meant for science and engineering students. A number of new courses were developed in support of this certificate, and it serves that population. I'm very happy about that. But to be honest with you, I'm much more proud, maybe that's not fair, I'm at least as proud of this, which is a program, another certificate, a certificate in energy technology and society that's meant for the humanities and social science kids. Because if you look at the history of Princeton, okay, the leaders that come out of Princeton, many of them are not majoring, much to my dismay, in science and engineering. They are coming out of the sciences, out of the humanities and social sciences. And they go on to be the CEOs of companies. They go on to be the Supreme Court justices. They go on to be the secretaries of state, okay? So those are the people that I want to reach at least as much as the scientists and engineers, because frankly, everybody in this room could go learn about energy technologies if you wanted. But a history major might not. And I'm delighted to say that the very first graduate of this program gave her senior thesis seminar last spring. And it was fantastic. It was she was a concentrator in history, and her topic for earning this certificate was the history of coal use in the UK and how that spawned the environmental movement in the UK. And it was incredible because you sat there listening and you could see, wow, okay, coal burning produces soot. And you cough, and you have a real strong visceral understanding of air pollution from coal burning. And so it was easy to see how that you would spawn the modern environmental movement in that way in the 1800s, early 1900s. However, think about the parallels with our situation today, where we have carbon emissions. They're invisible. They don't, carbon dioxide doesn't smell. It doesn't make you choke. It's in very limited concentrations, but think about the damage it does. And we have an enormous challenge to get ourselves onto the same, get our message out there about carbon dioxide and its problems by comparison to, the choking on soot. Okay, so, but it was wonderful because this history major is going off and is going to go work for an environmental firm. So she's the poster child for what I am very excited about with regard to this program. We also have a corporate affiliates program called Princeton E-Affiliates Partnership. Is Lynn Liu still here? Yes, she is. Lynn heads that program. She's the Associate Director for External Partnerships in the center, Professor of Chemical and Biological Engineering at Princeton. And we have a number of companies that we're interacting with, 2 utility companies, the largest utility company in New Jersey, PSEG, the one that, by the way, did the best during Hurricane Sandy, but anyway. And who has invested more heavily in renewables than any other utility in the country. It's surprising because it's New Jersey, right? But also with DuPont, with Lockheed Martin, with Southern Company, which is an electric utility as well as some small companies, and that we have a lot of ongoing both research efforts as well as partnerships with those companies, bringing them to campus, et cetera. If you're interested, I encourage you to go to our website about that. I mentioned the Technology Distillates Project, and the idea here, it came from going and talking to people on Capitol Hill, but what I realized is that it's not just Capitol Hill staffers that need educating. The public needs educating overall, and so in particular, one thing that we feel very strongly about is we want to be considered a trusted, honest broker. And so these distillates are being funded by private donations that from people who have no vested interest in the outcome of these assessments. And we post all conflicts of interest on the websites, And the idea really is that we want to provide. It's set up as a suite of articles about a particular subject that teaches. These are meant to be teaching documents that, a really smart, interested high school kid could go look at these and could get educated on a particular subject. But what if you weren't that high school kid? You were a sustainability officer in a company, and you wanted to just understand the economics behind some emerging energy technology. You could go read the article on the economics, because we cover, in very short articles, we teach you how to think about and ask the right questions about these energy technologies. So there's a part that has to do with key concepts, a part that has to do with the emerging energy technologies, so key concepts to be able to understand the technology, and then the economics, the policy, the environmental impacts, and you know, perhaps other things as we go along. So that's what this says here. A suite of short articles online. And the first one is on grid scale storage and its implications for renewable energy and adoption of renewable energy. So I urge you to go look at that at some point. Okay, so this is a slide that was put together as a result of one of our trustees, who's a professor at the Harvard Business School, listening to me talk about how I said, you know, in fact, I think about energy not in terms of one solution, but a portfolio of solutions that in fact are different over time. They will be solved over different time scales. And he said, oh, you should put that on a PowerPoint slide. And so here it is. Okay, so the point is, and you notice there are no numbers associated with that. So I'm not committing myself to particular time scales per se, but this is just my sense of the overall time frame for these different solutions. So on, you know, very near term, these things are already going on. Okay, the low-hanging fruit is really energy efficiency, and but there's still, the reason you have an orange box, by the way, for those of you that aren't in the cognoscenti, the colors of Princeton are orange and black. So the orange boxes are things that we're focusing on and or we have strengths in, and so. Energy efficiency, for example, in buildings and information technology and industry and vehicles, this is the low-hanging fruit. There's still engineering that needs to go on here, much, I would say, less science, but more engineering. Also, obviously, clean hydrofracking is incredibly important. There's still some interesting research problems that one can work on there, as well as electric vehicles. That's on the near term. The medium term, you know, is both cheap and efficient solar and wind. Okay, so those things don't often go together in the same sentence. So, so that's something that we have been emphasizing. Fuel cells, you know, safer nuclear power, smart grid. These are all very important. And if there's a box there, usually it means we have some, and it's not orange. We have people that work on that. It's just not necessarily a concentration. And then further along is biofuels, for example, which of course exists today, but I firmly believe that we should stop making ethanol from corn, and we can discuss that more in the break if you like. Carbon capture is not trivial. There are examples of carbon capture and sequestration, very, very important. We're going to be burning fossil fuels for a very long time to come, and if we can make progress on carbon capture, that's going to really help us in terms of hopefully minimizing the impact on the environment. But it's quite a bit further out in terms of the reason, even though you can read articles talking about making biofuels, but the amount that's being made is minuscule by comparison to the petroleum industry. And so this is, I have it out here this far because I'm thinking about when will it be practical. That's the idea. Okay, even further out, okay, is what I call solar fuels. So the further out you go, the more opportunities there are for chemists in terms of research that needs to be done. So solar fuels. Matt Cannon, who's here somewhere? Yes, where are you, Matt? Yes, works on this. I work on it. Certainly there are other people, I'm sure, in the audience that work on this, but the idea is to convert carbon dioxide to energy-dense liquids and to use solar energy. In my mind, it wouldn't even have to be, it doesn't have to be solar energy. It could be any renewable source. I don't care. I'm agnostic as to where the electrons come from, as long as they come from a renewable source. Grid scale storage. Oops, I hope I'm wrong that it's this far out, but we're there are examples of demonstration projects, but there is no large scale grid scale storage yet. Superconducting transmission, that would be much better than these high voltage DC lines I was talking about as well. We're definitely not there yet either. And then finally, fusion power. And actually, this box, fusion power, I think, I would love to see it moved over here, but it's never going to happen. to move it over there at the rate at which the federal government has decided or not decided to invest in fusion power. I like to talk about the amount of money that's invested in fusion power in units of B-2 bombers. Okay, so a B-2 bomber costs $2.1 billion, or at least it did the last time I was told how much it cost, which was a long time ago. But and the current fusion budget is $400 million a year. Okay, so we're talking about 20% of a B-2 bomber per year is what we spend on fusion. It means that on magnetic confinement fusion, and so it means that we may never get there. Okay, as a result of under spending. We can talk about the Lockheed Martin announcement later if you're interested. Okay, so in addition, we also work some on water desalination. That's clearly going to be an important piece of making sure there's enough fresh water for the world. And then, as I mentioned, really all the way along all these timelines, we have to be thinking about economics, policy, and behavior. We have to think about climate adaptation. We have a big effort actually in the architecture school and the civil engineering about climate adaptation and environmental pollutant detection and remediation. All of these areas are incredibly important. So this is actually a slide that's a bit of a repeat of what I just showed, just organized differently. This shows you, you can go to our research directory and you can see that we have over 100 faculty listed, and they're listed by theme. And so you can look up in any of these themes of energy efficiency, renewable energy, nuclear energy, whatever you like, you can find who's doing what on campus. And so there's a lot of work going on in a lot of different areas. Okay, I am noticing the time, so I'm going to skip through this pretty quickly and just say that we have catalyzed, one of the things I want to do with the seed money, you know, as I said, is to catalyze new directions and new ideas, high-risk ideas. And so what's shown, these are a whole bunch organized by theme. There's renewable energy, biofuels, et cetera. What's shown in blue are things that relate to chemistry, okay, of the kinds of projects that we funded. And so they relate to biofuels, they relate to combustion of biofuels, they relate to catalysis, photocatalysis, they relate to waste heat recovery, et cetera. There are lots of work on batteries and fuel cells, carbon capture and storage. There's a lot of work on energy efficiency, nothing blue here. It's not really so much a chemistry problem. Environmental engineering, so water cleanup as well as nitrogen. Actually, Francois, where are you? You're here somewhere? Yes? Yeah, so Francois is on one of these projects as well. Climate change and adaptation, behavior and decision making. I mentioned that we've just hired a really terrific postdoc. John Tully is not here, I think, but anyway, he came from Yale. And we're very excited about the work that he's going to do related to incentivizing sustainable behavior, and we're going to use the campus as a guinea pig. So what about the people? So there is this group of over 100 faculty that are involved, but we also have faculty lines. All the lines are split, so they're split between the Andlinger Center and other departments on campus. We have thus far hired 6 junior faculty, and they have been in strategic areas. So the first one is Dan Steingart. He works on energy storage, joint with mechanical and aerospace engineering. Next one was Barry Rand, who works on cheap solar cells and LED lighting, joint with electrical engineering. Claire White works on sustainable concrete and carbon capture and storage, joint with civil and environmental engineering. Forrest Meggers is joint with the School of Architecture and works on energy efficient building systems. Egeman Coleman just arrived, and he works on control of fusion plasmas, and he's actually joint with the Princeton Plasma Physics Lab, as well as mechanical and aerospace engineering. Princeton Plasma Physics Lab is, you know, the foremost magnetic confinement fusion lab in the country. The MIT people may not be happy about that statement, but at this point, that's the situation. Jose Avalos works is coming very soon, and he works on biofuels and biosynthesis of chemicals, and he's joint with chemical and biological engineering. We've had visiting faculty that I don't have time to go into. thought I would just spend a moment telling you about the research of some of our junior faculty who I think they've been hired because no pressure. I think they're going to help in a major way solve our energy and environmental problems. So I'm going to try to show this. This is actually an in situ picture of dendrite formation and cycling, actually, of dendrites in a battery that Dan is looking at. And what he's showing here is that by controlling the way in which the electrolyte flows, you can't really hope to totally suppress dendrite formation in cycling of batteries. But what you can hope is that you can make it reversible. And that's what he's showing here. So this is actually very exciting as an approach to getting to very high cycle batteries for long-term storage. And given the time, I think I'm going to go on to the next example. This is Barry Rand's work. One of the interesting problems associated with for example, photovoltaic materials, thin film photovoltaic materials, is that generally speaking they're deposited in a way that creates a lot of grain boundaries between small crystallites. And the grain boundaries tend to be sources where the carriers get trapped, and as a result you have less current, and so you have less power. And Barry has figured out ways to grow essentially much larger grains so that in a cheap way in thin films so that one should be able to get much higher currents out. So that's also very exciting. He's doing similar interesting things with LEDs. Claire White, it's important, you think, why did we hire somebody working on cement? Cement produces up to, on some estimates are 8% of all CO2 emissions, okay? Because of the process, it's high temperature, it releases CO2 from calcium carbonate going to calcium oxide, and so it's a non-trivial source of our problem. And so I viewed it as strategic, as did civil and environmental engineering. And so she does material science looking at essentially alternative materials that are low carbon emission cement technologies and understanding hopefully how they will properly age and not crack, okay, and age gracefully, shall we say. She also looks at materials for carbon capture. Forrest Meggers is a really amazingly gifted architect and engineer who has he's only been on campus for less than a year, and he's already catalyzed so many different interactions of people coming together to develop energy efficient building systems, as well as teaching undergraduates about it. This is actually one example of a project that was done this summer to come up with ways, very efficient ways of non-radiative cooling. I mentioned also fusion. So one of the things that's important, I work on one aspect of the fusion problem. I'm not a plasma physicist. I do material science work mostly. And the main issue, well, there are two main issues associated with bringing fusion power on board, in my opinion. One is the fact that you have to have some kind of way of containing the plasma, this very high temperature plasma that releases neutrons, and figuring out how you can contain it in something that will last for 40 years. That's really non-trivial, right? And the other is, of course, the economics. So we'll set aside the economics for a moment. I don't mean to trivialize that, but there are two ways of thinking about how to deal with the containment problem. One is to think about working on the materials that, well, maybe you can develop some clever way of having materials that can withstand the occasional blast from the plasma that leaks out of the magnetic bottle. And the other, and likely they will work work together, is using control theory and then manifesting itself in experiments to control and contain the plasma. And that's what Egeman Coleman does. So it turns out that you can use control theory that gives you, that takes measurements, uses feedback algorithms to figure out how to adjust the magnetic field in such a way that you can spread the heat to limit damage. And that's, in fact, without going into all the details, this picture sort of, gives you the idea of that in a standard configuration, for example, that's being built in France, in Yder, that you have what's called a diverter, where all of the particles end up going and creating damage. You end up with very large amounts of heat. And he has actually solved, in the course of his time as a staff scientist at General Atomics, has solved a non-trivial number of long-standing control problems to be able to essentially spread the heat. Very exciting. And he's a young guy, and he is a leader in the controls group in Yder, the Yder project being built in France. Last but not least, Jose Avalos, who has not yet joined us, is another guy who, again, I think these people are working on paradigm-shifting research that will essentially is taking a very different approach, using chemical reaction engineering to re-engineer what goes on in mitochondria of cells, such as yeast, to be able to produce. He's produced, for example, isobutanol, but also to eventually produce other value-added chemicals. So I think, again, this is a very exciting area as well. So he's the last of our junior faculty. We also have other projects. This is an intelligent Windows project that's going on. Again, I'm running out of time because I want to spend I have 2 minutes left. I want to spend 2 minutes talking about my own research. So just to give you a sense of how I spend my time not sleeping, I work on alternative photovoltaic materials, so cheap photovoltaic materials, most recently things like copper, zinc, tin sulfide, and essentially characterizing I'm a theorist, I use quantum mechanics techniques that I develop or borrow from others to characterize all the properties that are important in terms of developing an efficient photovoltaic. I have a project that's now coming to an end, but we did a lot of work related to how you can improve the efficiency of the cathodes in solid oxide fuel cells that are a very clean, efficient way to convert fuels to electricity. Fusion reactor wall, I work actually with so this project in particular, the fuel cells work and this fusion work, they're done as part of a team with experimentalists. And the fusion work is actually looking at, don't laugh, liquid lithium as a first wall material in the fusion reactor, and we can talk about that. There are very good reasons for looking at it, and we're doing work to characterize how the hydrogen isotopes involved in the fusion, how they interact with liquid lithium films. We also we have 2 projects related to photoelectrochemistry, one for water splitting, one for carbon dioxide reduction. We have a project that just ended related to biodiesel fuel combustion, and we work also on basic properties of lightweight metal alloys that could be incorporated into fuel-efficient vehicles. And last, we have a project that is just starting related to another way of doing solar energy conversion, namely essentially using, and this is joint with experimentalists, understanding how to use metal nanoparticles, and actually Lou Bruce, who I think is here somewhere, yes, he's on the team as well, to use metal nanoparticles to absorb visible light and use and what happens is that energy is converted into collective sloshing of electrons, so-called plasmons, that then when they decay, they produce hot electrons that can do chemistry. And so that's also a very exciting area. We have particular techniques that are unique in the world for being able to study the electronic excited states associated with that. So the very last thing I wanted to show you is just the front page of an executive summary associated with this distillate, the very first one that we launched, which came out in June. And I urge you to go to that website, and you can download the entire thing for yourself. That's a better rendering of the Andlinger Center. And I urge you to come visit us, to partner with us, and to, and hopefully the things that we're doing will inspire other efforts like this elsewhere. So with that, I thank you for your attention. I'd be happy to answer questions. Yes. David, do. Okay.
Oh, I'm sorry. One of the challenges with an interdisciplinary center is where people live. Will people have a home there with research labs and so forth, and then another home in their department, or will they be there for a while and then move? And so how do you, space is the last frontier, and it's often a challenge for interdisciplinary activity. I'm curious how you're approaching that.
Yes, so I would say it'll be interesting to see how it evolves. What the group of faculty, I was, when the gift came in that started this, I was on the committee that set down to define the program and to understand how the building would be designed. And we really wanted this to be a building where it was shared activities. And so people aren't, some people will have laboratory space, but it won't be necessarily their primary space. The idea is that we have themed labs, like we have an energy storage lab. And so there are at least 3 faculty that work on energy storage issues, and they will have the opportunity, that work on basically batteries and fuel cells, and they'll have the opportunity to have their students intermingled there, as well as equipment intermingled. So we have a lot of labs like that. We also have central facilities that are meant for the entire university. So there's going to be a 30,000 square foot clean room that will be used by everyone. Okay, that kind of thing.
So I'll bite on the Lockheed Martin thing. I think most, I'll admit I had no idea what you were talking about. So it sounded interesting. So what happened?
Well, there was an announcement by the president, I guess, I don't know, the CEO maybe of Lockheed Martin. How many of you saw that article? Is it only people that are thinking about fusion? Well, okay, so the announcement was that, look, you know, anytime I hear something like this, I'm so happy. I mean, I don't really care who provides the solutions. It doesn't have to be me. I just think it's our survival we're talking about. And whoever comes up with the solutions, fantastic, more power to them. So they made an announcement that they think their Skunk Works operation they feel has made a breakthrough in being able to come up with a way to have magnetic confinement fusion on the scale of a large truck, which is actually small, very small, okay? And it turns out that, so I was just talking maybe yesterday with or 2 days ago, with the deputy director of the Princeton Plasma Physics Lab about it, and just trying to understand the perspective. And what, look, it remains to be seen. We don't know exactly what they've come up with, but from what we understand and what he understood about what they were looking at, it was a design that was thought about 30 years ago and was abandoned. I guess it's possible that something has changed, and in fact they're one of our corporate partners, so we are very much hoping that if they've really come up with something that we can be helpful to them. They said that they thought that in 10 years they could maybe commercialize it. I mean, I would be ecstatic if that was true. I'm worried it's not, you know, I'm worried that it's unlikely. I hope it's true, okay? But from what we know right now, it's based on some ideas that had been explored and by the plasma physics community and then had been abandoned. So who knows, okay? But we have to learn more, and they're looking for partners. So I'm volunteering, you know.
Okay. Yeah, to me, the mission of the center sounds a lot like what I think our national laboratories are doing, which I think that's true.
Yes.
And so is there any design synergies between our national labs and your center?
Yeah, so Paul Alvisados, who is the director of the Lawrence Berkeley National Lab, is on my advisory board, and he 100% agrees with my philosophy about the fact that we have to have this broad portfolio. It's true that we are small by comparison to a national lab. I've never let that deter me in the past in terms of, you know, even though you're small, you can still have brilliant people and creative people that come up with solutions. solutions can come from anywhere. And so, the fact is that he launched this, what he called Carbon 2.0 program, and I think it's wonderful that they're doing that. And we have individual collaborations. We don't have formal agreements with these national labs at this point. I would be open to that. We've kind of eschewed having partnerships other than these corporate partnerships to start, because I wanted to get everything going on full bore, and I think as we get to steady state, we'll do more of that.